Welcome to the second day of DeepSec, to the conference. The first talk, I hope everybody is already awake, is about firmware cutting, and we are looking forward to the talk.
Thank you. So, good morning, everyone. How are you doing? Did you have some coffee? Yeah. Thank you for being here so early, and thank you for watching the stream. My name is Ferdi, and I analyze embedded systems. I am from South Germany, right here. And I like all kinds of embedded systems. So routers, wearables, industrial stuff, and vehicles. So can I ask you, raise your hand if you have some experience with embedded systems. Yeah? All right, though, so that's the majority. Well, we know that embedded systems can be very different. So let's talk a little bit about, what kind of devices we could be looking at. So there's the type 1 devices, which run some kind of operating system with one or several applications on top of it. And there are type 2 and type 3 devices. So these are devices that run either some kind of real-time operating system or no operating system at all, like some kind of while loop, essentially. So here on the right, you can see that this is like a very typical sensor, a very small control unit. All it does, it reads some values and puts it on a CAN bus, for example. So this would be a type 3 device. And then you have very fancy devices that can be both, right? So this is a modem, I think, LTE and GNSS. And in this talk, we will focus on type 2 and type 3 devices. This is not my definition. This is from Munch and others, but I think it fits very well. So when we get these kind of devices, we need a couple things, right? We want to find bugs. We want to find bugs, so the first thing we need to do is we tear them apart, we look at what is inside, and then we try to get the firmware. So in these two phases, the dominant factors are if you have the right equipment and the right skills. So for the course of this talk, let's just assume that you can buy equipment and that you can take training to get the skills that you need. So once you have the firmware, the equipment becomes a bit less important because you work on a laptop and you reverse engineer the system. So you need to know some facts to get started. You need to know the target architecture, of course. You need to know the memory map, where the peripherals live in memory, and so on. And you could say that this is easy, but of course, we will see in which cases it is not that easy. And we will focus on the firmware analysis and exploitation part. So, as I said, it's not always that easy. So what if, for example, the system safety features work against us? Yeah, so you have devices that need to be fail-safe. So if there's a faulty component, the device will have some mechanisms that try to prevent complete failure, probably reset the system. And also, we don't always have the equipment that we need. For example, sometimes you can't buy things anymore, or things are not documented, or you need to sign an NDA. And we will try to solve these problems. Okay? So let's start with the first one, which is about figuring out what these safety parts of the systems do and how we can get around them so we can do our analysis. This is inspired by a lot of my work I did on automotive systems. However, you will find these mechanisms or these concepts elsewhere. And in this example, we have a microcontroller which we want to analyze. and we have some kind of peripheral microcontroller or a specific watchdog circuit that expects a periodic signal to know that everything is still fine. If it doesn't get that signal, it will reset the microcontroller, hoping to prevent complete failure of the component of the system. Now, the microcontroller is still connected to the network on its own, but the problem is if we try to debug this guy here, eventually, you hit a breakpoint and you inspect some values, the watchdog window is going to be missed, so the watchdog will destroy your session. There is another circuit or schematic like this, where you have this system basis chip, which integrates a number of functions into one integrated component. So here, the difference is the network connects, or the microcontroller connects to the network through this SBC. So how do we get around this? Well, the first one is easy. You just prevent this peripheral or this watchdog to reset the microcontroller, and this works in many cases. However, for the second case, it's not that easy, because the failure condition will be detected by the SBC nonetheless, even if you cut the reset line. So it's going to try to prevent, or it's going to try to protect the network against this faulty component here. Okay? So there's a variety of options you can do to try to convince the watchdog everything is still okay. There are special debugging modes, or you could be man-in-the-middling this, and or you replace the component completely like this. Yeah, so you remove the SBC, and you put your own device there, which emulates the SBC. Now, these options all have their pros and cons, of course, but this is not black magic. This is something you can pull off, right? So let's say that we've solved this problem, okay? Now we want to debug, but still we lack equipment, or we might lack critical information. In some cases, you're completely in the blind. You only have code execution, for example, but you don't know where peripherals are mapped because you're handling a customized piece of silicon. So let's look at these cases. Also, debugging pins might not be present or used for something else, because systems designers try to integrate as much as possible into the cheapest device family option or package that they get. So if they can save some space, they will do that. Pardon me. Now, even if you do have debugging access, sometimes, or with some protocols or peripherals, it's not possible to do it interactively, because you have some fast radio communications or fast networks that expect some timing guarantees. And once you debug, it's not gonna, you'll break the protocol just by debugging it. So let's look at how this can be solved. We can either choose to do a hardware debugging, which has the issues I just described, or we extract the firmware and emulate it. And either of these options might work, and there's tools that handle them, but as I said, debugging suffers from disrupting the target if you do it interactively, and it could also be a lot of work, or maybe you just don't have the equipment. And in emulation, you might not be able to fully emulate all aspects of the system, because we're handling embedded devices, right? They will be talking to peripherals, they'll be, running some kind of RTOS, and that sometimes is very hard to solve in emulation. Now, I know people that can do this easily, and I'm not saying that emulation is bad, but my goal here was to find some kind of middle ground right here. So how do we implement this middle ground? I'm presenting FLOPS, which is a firmware liberation framework on Python. It's meant to patch and instrument raw firmware, adding trace capabilities and backdoors. So you can put breakpoints or trace function calls interactively, with the goal being to do this on the real hardware, on the real system, maybe in a network, not disrupting the actual functionality of the firmware. It is based around this assembler that we wrote in pure Python, which does PowerPC, in this case VLE only, thumb mode for ARM, RISC-V, and Intel architecture, which right now is still a little bit, mushy, but we'll get there in a few weeks. So you might think that this is an odd choice of architectures, but it's not, because we deal with a lot of devices that support these. And for example, while some processors, especially in the automotive world, support VLE, they don't support the full Book E specification of PowerPC. So this is why we choose these smaller or these extensions, right? While some other processors support the full ARM instruction set, they will also probably support thumb mode, but it's not the other way around. So this way you can use this on Cortex devices, for example, which is a very broad range of devices. Now, in order to use flops, you need to have knowledge of the target architecture, of course. You need firmware read-write access, which is a lot to ask for, but it can be achieved. And you need to have some channel for transferring data. You're instrumenting the firmware, and the firmware has to talk to your computer somehow. Also, of course, you need the computer itself and some kind of disassembler. Now, this is a design decision. We specifically said that we will use some other disassembler and didn't implement this ourselves, simply as to not reinvent the wheel. And again, our goal is to make firmware instrumentation very easy. So let's look at the individual components a little bit. But before that, let's discuss, because there's other projects doing assembly, right? So we have Keystone, which is based around LLVM, and because of that, it supports a large range of architectures. But we found that adding architectures beyond LLVM support can be tricky, and also we would like to have a little bit more high-level functionality, such as reusing payloads that we write in assembly. Of course, there's other tools like Radar or Ryzen, but these have the same issue. They typically expect a string of instructions and turns it into assembly code, and they do just fine, But in our case, we would like to make it a bit more dynamic and think about payload reusability, because you don't want to be writing assembly for every target that you get in your project. So this is an example. It's very arbitrary. I'm not trying to pick on a particular project here, but essentially this is how you would programmatically generate shellcode or assembly instructions in R2. Yeah? So you select the architecture, you make some kind of command, you pass assembly as a string, and then it gives you the bytes representing these instructions. So this works just fine, but we do it a little bit differently. So in flops, you have to import a bunch of stuff, and everything is an object. So you have this shellcode object, which might also be a module or a function, each with their own nice properties, but they all have an address in memory that you can assign or automatically assign, and they have a list of instructions. So notice that we support the native instructions as they are specified in, well, the language or assembly manual for this type of architecture. And we have cores. So note that this doesn't actually say PowerPC. This says E200Z, whatever. So we can model cores with like special registers, because each of them have like slight differences. And if we can model that, that'd be great, right? So Also, we support these auto instructions, which make it a bit less painful to do certain things that you do very often. So, for example, loading an immediate, you don't want to memorize the specific assembly instructions for those. You just want this auto instruction that notices, okay, this is a 4-byte value. I need to generate like 1 or 2 native instructions to put this in register 5 in this case. And going further, we can have labels with references, right? So in this case, if something is less, you do a compare, and that compare is resolved once the address of the label bailout is known. Flops is a 3-component architecture. You have the disassembler that I mentioned. This is Ghidra, and I will show this later in a demo. And everything resolves around this JSON configuration file, which says at which addresses in the binary to patch and instrument and dump data. So you do that from Ghidra. You can use any other tool, but we have a plugin for Ghidra that does it. Once you have this JSON configuration, you hand it over to the patcher, and the patcher reads the original binaries, patches them according to the specification here in the configuration file, and generates instrumented binaries. These binaries, you take them, you put them back on your target, and then you have a small listener component which takes care of handling the target at runtime and logging events or reacting to events. So how does our instrumentation work? Essentially, we need to answer 3 questions. How do we gain control over execution cleanly, right? We don't want to interrupt the target. We want to make sure that it works as untouched as possible, let's say. Where do we put the extra data? This is static instrumentation. So we need extra code to do what we want, right? And this code has to go somewhere. And finally, how do we communicate with the target? So we'll go through this step by step. Redirecting control flow is done by the trampoline. So we have 2 methods for this. The first one is selecting a target instruction that is big enough and replacing it with this. We take the original instruction, remove it, and insert a jump to our slice gadget, which essentially saves all the registers that we're going to use in our instrumentation. Once it's done, it's going to jump to a configuration-specific code. Remember how we have this JSON config file that has entries for each location that we want to patch. And on each location, you can have a different configuration. For example, some location just dumps 2 registers. The other location dumps a bit of memory too. So for each of these configurations, we generate the code and hand it over to this data IO function, whose only purpose is to actually dump data to our computer. Note how this function doesn't return here. It returns to the slice-specific code, which then runs the original instruction and returns back into the original code once it's done. And I don't think this is something new. This has been done many times, but we find this to work really well across many architectures. The second one is decorruption. This is a bit more tricky because remember how in the trampoline we replace an instruction with a long jump. This jump is usually very far, so you can't put it anywhere because some instructions are probably just very small and you don't have the space to do it. So if for some reason the trampoline doesn't work, you can corrupt your target instruction so that an exception is generated by the processor. And this will invoke a fault handler, which then determines the location of the fault and redirects our control flow back to whatever I described for the trampoline. So this is a bit more tricky to implement, and I believe this has been shown in several other works too. However, we actually found this to work across architectures because usually every processor has some kind of special exception for invalid instructions. So this works too. It is slower than the trampoline, so you should prefer the trampoline in any case. But we do give you this option too. Now, all of these orange boxes consist of assembly code that has to be written. So you'll be asking if we can reuse some of these blocks, right? And the answer is yes. It depends. So these ones here are, again, in charge of saving registers, preparing state for our instrumentation, so we can reuse them within the architecture. They don't depend on the exact processor family that you're on. So we can put them in a Python module, save them somewhere. Now, these other blocks here, especially the data function, is dependent on the IP that you're talking to in the microcontroller. So chip manufacturers are not going to reinvent the wheel for every processor family, so they will reuse this peripheral IP. And while they don't reuse it everywhere and make slight modifications, we can try to also make like a small packet or module that we can import whenever we know for sure that the same peripheral is used. And the same goes for the fault handler over here. So those are usually similar. As for the rest, we try to generate these dynamically and reuse them within the architecture, because putting data from place A to B and then invoking a function is something you could call generic if you architect it the right way. So now that we know how to gain control over execution, where do we put the actual data? You know, we generate events. Where do they go? For code, it's easy, because many devices are over-provisioned or use modern microcontrollers that have a lot of space, so we can almost always find some space in the flash where we can put our extra code, even if it's limited. It is an option. So for RAM, it is a bit more tricky, because we have volatile data, and we can't always reason about whether some place in RAM is safe to store this data that we generate. So one answer to this is peripheral memory. This picture here shows the FlexCan IP block on the Bolero series devices. And while this may sound a little bit hacky, it works really well, because these devices have large buffers for CAN messages in this case, but things like Ethernet or USB work just as fine. And designers typically only use one or two of these blocks, and the rest are just disabled. So as long as our peripheral is clocked, we can use, in this case, a whopping 1 kilobyte of memory just for our instrumentation. And figuring out if something is used or not on the peripheral side is actually, it's possible. It's not black magic. So this actually gives us memory where we can cache values, coverage maps, etc. Of course, if you know that some place in RAM is available, you can use the RAM, because for peripherals, all the accesses have to go over the peripheral bus, so you could argue that it's not going to be as fast, but it does give you way more options. This device here, for example, has 6 of these FlexCan blocks, so while it's only using 1. So we should definitely make use of that. Finally, how do we communicate with a target? We need to have some kind of data channel, right? And the answer to this is it doesn't matter too much. You have these very simple protocols like UART that require a low amount of pins. If you have some extra pins available on your target system, then you can use these. Or, of course, you should prefer the faster ones, which are Ethernet, SPI, CAN, of course. And these are faster, a bit more complex to set up on the assembly side. And the downside is they require more pins. So the general answer to this is that you should use the interface that works, the interface that is available. And FLOPS doesn't make any assumptions about which interface you use. It just gives you, it just expects some data to be coming in, like raw bytes. That's all. So this is something you need to decide for every specific target that you have. On this specific target, I can show you something interesting. We want to let the hardware do the job for us in almost every cases, right? Because we don't want to block execution of our target code just for getting some data out of the system. So what you see here is a message slot that we prepare with a CAN arbitration identifier, and we have 8 bytes in this case, but of course, CANFD, you have up to 64. The idea here is that we steal this slot from the application because it's not using it, or it's using it on an identifier that it doesn't care about, or is not present on the network in our testing case, and we fill it up. Oh, come on. We fill it up with data, and as soon as we have packed the buffer, we transmit. And then transmitting consists of setting a bit somewhere here and saying this message is ready to go on the bus. And once it does that, the hardware will take care of arbitrating this and sending the data out, so the application doesn't have to handle all this. While this is being sent on the bus, we can take the next slot and fill it up with data too. Notice how the identifier here is a bit higher than this one, because we want this one to go out first. Yes, we do them in sequence. And this is an example. You can also knock yourself out and do DMA and all kinds of stuff, but usually you have some kind of time budget that you can spend on making this as fancy as you want. So in many cases, you are just fine too, depending on your goal. So the listener is the third component, and it will handle links such as UART or CAN or SPI, as long as you define some kind of protocol, because not everyone needs certain information, so this is something you have to do yourself. And this protocol generates events that are either non-interactive, like I just executed a function, put that in the log file, or interactive events, such as breakpoints, where you can drop into an interactive shell and read and write memory and so on. Now let's look at this ECU that I brought here. It is a rather harmless example, but it's from a premium segment body application. It has the safety functions that I mentioned, has an SBC. It's very common, It has a large amount of generated code, like many modern control units. Of course, it's using some kind of RTOS, and it uses a VLE-only processor core. Now, you can argue that the MPC56 is a little bit dated, but it doesn't change the fact that it uses VLE, like the modern successors of this device, and it just represents these types of devices really well. So, come on. Let's look at what I have prepared here. We will first look at how to instrument stuff in Ghidra, generating the configuration file. So this is like your regular disassembly, and Flops will add a panel on the right here. So I have prepared the configuration already here. You can navigate the functions that it instruments by clicking on them. And if I want to instrument another function, you would go here, right-click, see the Flops menu here, and then choose one of these functions. In this case, we will just hit instrument function, and it will label that and create an entry here on our configuration file, which you can then save. Okay? You need to define a couple other things here, but we don't actually have the time to go into that. So, of course, you can also select multiple functions and instrument them like this. It only instrumented one because I already selected this. Anyhow, once you have that configuration file, you hand it over to the patcher, and then the patcher instruments the binary, of course, and flashes it, which is something I already did to save some time. So let's head over to Linux here, where we have 3 windows. On the right here, I will start the listener, which listens over CAN for any instrumentation-generated messages that this device will send. Okay. So let's look at this first. We have the raw CAN dump here. which is just some raw traffic to keep the device alive. So if I turn on the power, you can see there's a lot of stuff going on because, of course, we instrumented not everything in the firmware, but a very large part. So for example, we removed the bootloader, and I have gone ahead and also removed some of the noisy things in the firmware that we don't care about in this case. But let's say we care about diagnostics, right? Because it is a big attack surface for automotive systems like this. So let's start the listener. And on the bottom left here, I have a small script that enumerates some things on UDS. So when I need to start this too. Yeah. When I power it on, you can see that we get the instrumentation events on the right. And if I had this big enter button, it's going to be very awkward if it doesn't work. And it doesn't work. Let's try one more time. Yeah, it's a bit noisy. But the point here is that once you do these things, you can interact with the target live and see if any of the events change, like this, okay? So it's not much happening here. It's just trying read data by ID a bunch of times. But if you capture a log without this diagnostic interaction and then compare it to a log where you do enumerate some UDS things, of course, you can take it back to Ghidra and label all the functions that were discovered in the log with the diagnostic stuff. Okay, so this helps us reverse engineering, and of course, you can take it further and try to find some bugs this way. So really, this was to show that it works on a real device. Yeah, let's skip these. So at the end of the day, we get paid for finding bugs and helping them fix them. And this is where it gets a little bit fuzzy. So for flops to be applicable for fuzzing or in general scanning, you need to define a fuzz entry and an exit, because these are very dynamic systems with real-time operating system, etc. So ideally, you know what you're looking for already. So you have some kind of entry point, and from there, you activate the instrumentation so that you don't log everything that happens before that point in time. You can do snapshot fuzzing by saving the state on the computer and restoring it using the computer, streaming it into your vector that you put there using flops. But snapshot fuzzing is broken by specific peripheral interaction. So it's perfect for things where you have like a library or a parser, but it doesn't work really well, or you need to watch out for a lot of things if you just do this on the target like I just did, right? So if I try to restore the state, after I've dealt with CAN, with peripherals, with diagnostics a little bit, we might actually break the functionality a little bit. So we have to be careful there. Of course, instrumenting all fault handlers is important. These devices don't have a fancy MMU as you would find in Type 1 devices, or if they have an MMU, it's not going to be as fancy, let's say. So whenever you get a crash, it could mean a variety of things, and you need to be careful about differentiating them. In the general case, these crashes don't imply bugs, and there's a big body of work that analyzes this and reasons about, how to properly detect bugs. I have picked out a couple examples that I would like to quickly talk about, which is heap corruptions and double freeze. Everything based around malloc can be instrumented, of course, and this is one of the easier examples that I would propose. However, when you go a bit deeper and you want to also detect stack corruptions, you do it the same way. You append and prepend some canary values that you validate at function exit. This is already a bit more intrusive because you have to instrument both function entry and function exit on all functions that you want to sanitize, so to say. But it's still possible. The big issue here is that devices like these don't typically have malloc at all, because they, the designers need to follow some standards, and you don't really find that dynamic allocation a lot. Rather, of course it exists, but rather you will find static allocated memory, and it's a bit harder to reason about how to find bugs there. But some example that I do want to mention is, if you know for sure where pointers are statically allocated, and you are sure that these locations in the RAM are not used for anything else, then you can define your fuzz entry, your fuzz exit, and afterwards try to sanitize the values there. So if they point to something that isn't mapped in memory, you know for sure that you broke something. And you know, in general, you can't rule out false positives using this method, but by doing this a couple times, a couple cycles, and reverse engineering, you still have the options to do application-specific checks like this. And it works. So, summarizing, flops is an assembler toolkit written in Python. It's for embedded security applications, mostly focused on debugging and reverse engineering, but also usable for fuzzing. We use it to patch and instrument black box firmware image without preconditions. So you don't need a tool chain. All you need is some assembly payloads, and of course, the device itself, right? We've compared it to alternatives, like alternative tools or to emulation, and it's limited mostly by how much flash you have available and how fast the data channel is that you're using. This is gradually being open source, so not everything is available yet, but right now the focus is on getting the assembler up and running, and all these things are tested. So we have unit tests, and of course your feedback is very much welcome. And with this, I think we can go over to the questions. Thank you.
Thank you. Questions? I've got a microphone with a big handle. Then a question from me. Yeah. For every change in the instrumentation, you have to reflash and restart the target, if I understood this correctly.
Correct.
Yeah. Okay, so the process is rather big turnaround times. Yeah. It's not meant to do this 1,000 times, because eventually you will also wear out the flash. So yes, of course. You try to instrument as much as possible, flash it once, and of course you can implement some flags, for example, disable this or enable this. That is something you can do. Yeah. Oh, okay. And then a second question, many of these chips are often, at least from the time I did something in that direction, mask programmed, so you can't really find an easy entry point. Is this hard today, or? You mean for getting access especially
to
in automotive, you have devices where you really don't have an old-fashioned flash memory, but the chip has, at least for the first startup sequence, is in the mask of the processor, so you really can't change anything. Yeah. So processors have boot ROMs that take care of the very, very low-level initialization of the chip. But in this case, we care about the application, and the application is flashed into the device by some machine at the assembly line, or some poor, soul like doing this 1,000 times a day. So we do focus on those. We don't, of course, you can't instrument boot ROMs with this, because these are read-only, as you know, or you have to make a lot of effort to be able to modify them, like physically on the device. That's okay. Yeah. Questions from I'm just looking if there is something come up in the chat. Oops, sorry. No, nothing in the chat. So thank you. And you can take off something to the coffee break, which is after the next talk. Thank you. Yeah, I'll be around for a while, so I hope to talk to you. Thank you.